Hello, good morning everyone. Welcome back to Physics 102 class. Today we are going to look into one of the most foundational concepts in physics, that is forces in nature. If we want to understand how anything in the universe moves, interacts, or even exists in a stable state, we need to understand the fundamental forces that governs it. Okay? Now, from the definition of a force, it is not just a simple or precise physical concept. Okay, a force from definition can be defined as any interaction that can change or tend to change the position of an object. For instance, let's take a case. When we talk about the state of rest or uniform motion of an object, this is what we traditionally think of with the Newton's law, if you recall. Okay, the state of a rest or a uniform motion of an object, that is when there is no action of any force. So Newton's law governs the details about the force with that effect. Okay, so making things start moving, slow down, or change their velocity. Okay, so all these can be referred to a state of rest or uniform motion of an object. The second case, an object or shape or size can be changed by applying a force. For instance, now if we take a case, squeezing a rubber ball, or stretching a spring. Okay, so whenever we stretch a spring or we squeeze a rubber, we apply a force to change the object's shape and size. Okay, so whenever you see an acceleration, a deceleration, or a physical deformation, there is an action of a force. In other words, a force is actively involved in that scenario. Okay, so from what we are going to explain today, there are four fundamental forces in nature. We have the gravitational, we have the electromagnetic, we have the strong nuclear, and we have the weak nuclear force. All these are fundamental forces in nature. Any other force, like a friction, tension, normal, are emergent forces. They arise from the four fundamental forces we have in our physics case. Okay, so in daily life we mostly experience gravitational and electromagnetic force. You will see the reason. Now, where do these forces come from? This is a very big question and interesting. Where do these forces come from? Okay, in nature there are four fundamental forces, as we mentioned, and in our day-to-day life we have been more interested, we have been more engaged with the gravitational and electromagnetic forces, as I mentioned. So let's take them one after the other, as you can see from the table on my slide. Number one, gravitational force. Okay, we have been thought about gravity, the influence of a force that pull an object down or attract an object. This is by nature is called a gravitational force, and it's purely attractive. It pulls an object but never push it up. It is always attractive. Okay, so the relative strength, for comparison, we define its strength as 1, making it one of the weakest fundamental force, and it has an infinite range. So that is, every single piece of mass in the entire universe is attracting every other piece, regardless of how far or apart they are. Okay, then acts on what property does it care about? Mass, to energy. So if an object has a mass, gravity normally affects it. Okay, so you have to take note of this. Then going to number 2 very quickly is electromagnetic force. Well, by nature, unlike gravity, this can be both attractive or repulsive. And the relative strength is about 10 to the power of 36, stronger than the gravity. So this is massive, and this is massive difference, and it's why a tiny magnet can easily pick up a pin or a paper clip against the gravitational pull of the entire planet Earth. When you have a very small magnet and you try to attract a very small iron fin, it will lift it up from the ground, so it goes against the gravitational pull of the entire universe, Earth. Okay, so it has an infinite range also, and the key property for this actually is electric charge. No charge, no electromagnetic force. So as we can see now from the slides, a proton and electron attract each other with a gravitational force, but they also attract each other with electromagnetic force. So between two protons, the electrostatic repulsion is about 10 to the power 36 times stronger than their gravitational attraction. So what this is telling us, this is simple fact, is exactly why atoms are held tightly together, and fundamentally why our pits, don't pulse straight through the flow, because of the what? The force of attraction, Okay, so this is important, and it's very necessary to recall this in trying to understand the fundamental behind knowledge behind this electromagnetic attraction or repulsion. Then going to number 3 is strong nuclear force. In nature, it is an incredibly powerful attractive force, but the relative strength is big, approximately to the power of 36, 10 to the power of 38, sorry. It is the strongest force known to physics for a long time, and it has a range, around, is extremely short in terms of the range. So it only operates on a subatomic scale of about approximately 1 femtometer, that is 10 to the power minus 15. Okay, that is roughly the physical size of an atomic nucleus. So the applications on the quarks and the nucleons, like protons and neutrons, this force is within the subatomic. It acts like a glue, that binds protons and the neutrons together inside the nucleus, and successfully overcoming the massive electrostatic repulsion that may arise or trying to push those positively charged protons apart. Okay, then number 4, one of the fundamental is the weak nuclear force. It can be attractive by nature or repulsive, and it has a relative strength around 10 to the power of 25. It's much stronger than the gravity as well, but vastly weaker than the electromagnetic and strong forces that exist. So it has even a shorter range than the strong force, but it operates at about 10 to the power minus 18, which is smaller than the diameter of a single proton. It acts on quarks and leptons, like electrons and neutrinos. Okay, so we have to pay attention to some mathematical formulations related to these forces. Usually, it is a universal force when we talk of gravity, as we mentioned previously. So every mass attracts every other mass. It is what holds the planets or orbits and create the ocean tides. So gravitational force is very powerful, and one of the fundamental force that was examined from the mathematical formulations based on the Newton's law of gravitation. And you recall the formula given is Fg, which is equals to G multiplied by the M1, M2. These are the two masses. That is when there is an attraction between the two masses, and inversely proportional to their distance. So the force Fg is directly proportional to this product of the masses, and inversely proportional to the square of the distance between their centers. Okay. The constant of proportionality G here is the universal gravitational constant, which is normally given as 6.67 to the power of 10 to the power minus 11 Newton meter square per kilogram square. This is incredibly tiny fraction in another mathematical reflections of why gravity is so weak on the fundamental scale. Okay. Also on the right side, you can see the Coulomb's law. This is electromagnetic force, as we mentioned. This force acts exclusively between electric charges and can be attractive or repulsive, as we mentioned. And this single force is responsible for almost everything we encounter in our daily life outside of gravity. All of chemistry, all material science, and even the lights you are using to see right now are form of electromagnetism. So it's very important force in our day-to-day life. So the formulations based on the Coulomb's law is that Fe is equals to 1 to the power of 4 pi epsilon naught by multiplied by Q1 Q2. Okay, and it follows the proportionality, inverse proportionality, the square of the distance. That is the product of the two charges Q1 and Q2 is inversely proportional to the square of the distance. Okay, so however, because charges can be negative, the force can be positive, repulsive, or negative, attractive. So as clearly shown in the diagram, you can see that, for instance, like charges repel while opposite charges attract. Okay, this is very common, as we know from our elementary physics. So the constant epsilon naught here is actually the permittivity of free space, the constant value of 8.8 to the power of minus 12, as we all know. Okay, now the next one in details is about the strong nuclear force, as we just mentioned now. It has a short range, as we mentioned previously, but is very strong in relative strength. Okay, it holds the nucleus together and acts identically between protons and protons, or neutrons and neutrons, or even protons and neutrons. It binds these particles together tightly. Without this force, the universe would have not, come into maybe a composition as an entity. Because why? What will happen if there is no this force, action of this force? The universe will have no atoms other than simple hydrogen. Okay, this is the reason. Okay, so the last one is the weak nuclear force. Compared to the strong force, is very weak, but is absolutely critical. It's responsible for certain types of decay. Radioactive decay, mostly the famous beta decay. So from nuclear equation below, you can see that a neutral neutron decays into three distinct particles: a proton, an electron, and electron antineutrino. Okay, so the weak nuclear force is what controls those subatomic transformation, allowing one type of particles to change into another. Okay, so it's very important to take note of all this, as you can see now. So I will give you an example now. For instance, the friction you feel when rubbing two objects together is actually just the electromagnetic interaction between the surface atoms that exist. Okay, the tension, for instance, if we stretch a spring or string, it's just what it's telling you is just the electromagnetic bonds between the string molecules resisting being pulled apart. So that is the transformation of the force. So when we say a tension, we are talking about electromagnetic bonds between the strings of the molecules that are being resisting this pulling apart. Okay, so every microscopic force simplifies down to this force. That is why I told you from the beginning, all other forces in nature, like friction, tension, normal force, are emergent forces. They arise from the four fundamental forces. So in daily life, we mostly experience gravitational and electromagnetic forces. These are the two most distinct forces that are being experienced in our daily life. Okay. So because the strong and weak forces have such incredible short range, they locked away inside the subatomic worlds. So the microscopic world that we live in today, for instance, everything we can see, touch, or even some applications in mechanical system and engineering is entirely ruled by gravity and electromagnetism. Okay, so at the end, I want you to remember that all other forces can act as non-contact forces, operating as action at a distance. I'll give you an example now. A magnet pulls iron, a bar of magnet, for instance, pulls the iron without touching it. When you try to move a magnet close to a pin, maybe a metal screw, you see that the magnet is what is pulling the iron, without touching it. Okay, so this is what we call action at a distance. Okay, another example is the Earth holds the moon in orbit across empty space. They are all field forces which set up our what foundational field. Next foundational field maybe when we are going to talk about the electric fields in the subsequent lecture. Okay, so it's very clear to understand the influence of these natural forces that we have as fundamental ones. So by definition, you know that is any interaction, when we talk of force, is any interaction that can change or tends to change the state of rest or a uniform motion of an object, or it is shape, or to change its shape or size. Okay, so for today, I think this is the slide, but let me quickly send you a very short reminders in the next slide so that we can close. I observed that the previous lecture took about 30 minutes, so this one, for the sake of upload, maybe we'll try to limit within around that 20 minutes, which is very okay before our subsequent lecture. Okay, so if you look at this slide, it's just like a summary of what we have just treated with some key points and also some kind of, questions that you can easily recall, especially during the assessment. So key points here, for instance, we are talking about charge is property of matter. We don't have problem with this. We know about this. So it can be positive or negative. It is conserved and quantized. Well, what we mean by charge is conserved. It means the total electric charge in an isolated system never changes. It can only be moved around or split between objects, but the algebraic sum of all charges stays constant. In other words, conservation means a charge cannot be created or destroyed in any process, only transferred between particles or locations. Okay, so practically, if one object loses electron, definitely another one gains exactly that number of electrons, so that the total charge is unchanged. This is what we mean by a charge is conserved. Okay, when we said a charge is quantized, it means, for instance, electric charge appears only in discrete packets. Every observed net charge is an integer, multiple of basic units. Okay, so elementary charge E, as we know, about 1.602 to the power minus 19 coulombs. Okay, therefore, quantization means measured charge counts in whole number, multiples of elementary charge. So we can give a formula: Q is equals to NE with integer, where N is integer, positive, negative, or even zero. Okay, so take note of this conserved and quantized explanation. Okay, next, understanding the charge is the foundation of electricity and magnetism. So based on this, we give an example. One example, you can see a glass rod rubbed with the silk that loses about 1 to the power of power 12 electrons. So we have to find the net charge on the rod. Solution was given and Q was found because Q is the charge lost by the rod. Okay, and then the number of electrons, which is equals to n, is given as 1 to the power minus 12. So you can just have a direct substitution here and multiply and get your Q. Since electrons are lost, rod becomes what? Positively charged. So what gets the electrons now is the iron rod. Also is the rubber rod. Okay, and the Q is what's found. Some checks for yourself. What is the SI unit of a charge? Is given here as column. Can charge be created? No. It can only be transferred, as we mentioned just now. It can neither be created nor destroyed. Okay, number 3, it said name 3 methods of charging with examples. We have friction, conduction, induction. We are coming to this in our subsequent lecture. So number 4, why do like charges repel? Due to the force of repulsion between them. Then finally, what happens when a charged body is grounded? Yeah, excess charge flows to and from the earth. So when a charged body is grounded, there is what? Excess flows from the what? From the earth. Yeah, so we have some fun. Physics is just like a fan. Okay, a tiny plastic cone can attract small piece of paper after rubbing your hair. This is what we have been experiencing right from our childhood experiments. So this is nothing but what we call electrostatics. Charges at work in every life. Okay, so there are some areas of application. The lightning, build-up charges in the cloud, discharge due to induction. That is why we are using the earth in our buildings to trap this the build-up charges in the cloud coming from the cloud. We have the use of static charges to attract toner particles using a photocopier, the printers we are using. The spray painting charge particles, charge paint particles are attracted to grounded objects. So all these are what some of the areas of applications. And in summary, charge exists in 2 forms, as we mentioned. It's quantized, charge is conserved. The 3 methods of charging, friction and conduction, induction, all these have been explained in details in the course of this lecture. So I think for today, to save much of our space, maybe we can stop here until we meet in the subsequent lecture. Thank you very much for listening, and I wish you all the best. Thank you very much. Bye bye.